Today's pretty much in your court, whatever questions you guys have. I've loaded up all of the homeworks in here, like in the past. And so let's see what you got. Yes. Sure. This section here on homework 12, yes. I want to, in order to kind of, also, we can, there's not that much in terms of these three homeworks. So what is it, like if you started at the beginning of any one of these questions, where is it that your brain says, okay, I don't follow what that means? Hmm. Yeah. Okay. Yeah. So after you do the matrix multiplication, which we'll do, I brought the matrix, it's in here. Then it's a, s- it comes out close to a scale of 0 to 1. Okay. And you can truncate it like if it goes over 1, you can just stop it at 1. If it's negative for whatever reason, you can stop it at 0. So you just cut off any values that are greater than 0 to 1 and then multiply by 255. That's the last step. So let's go ahead and do that. So here's the matrix that those companies that I've talked about, Microsoft and Adobe and all of that, all of those companies decided on this matrix in particular to convert the XYZ to RGB values. And so it's left multiplied. So that means that we take this first row, once I find my pen, we take this first row and multiply by this column, and that gives us the R value. We add it together. And so let's see, let me make sure that it's the same one. 13, yeah, 13. And so for 13, we have zero point 0.7, zero point 0.64, and 0.09. So the R is equal to 3.2410 times zero point 0.7 plus, or I'd say a negative, negative, let's do that since it's negative, minus 1.5374 times zero point 0.64 minus 0.4986 times the 0.09. This is why I like spreadsheets, because you can just hammer this out a lot faster. And then one, enter 0.64 times minus, and then 0.4986, enter 0.09 times minus. Okay. And I get 1.24. Is that what you guys got? Yeah. So this is equal to 1.24. Okay. Now G is the second row times the first column gives you the first column, second row value here. So this is minus 0.9692 times zero point 0.7 plus 1.876 times zero point 0.64 plus 0.0416 times 0.09. 9692, change that, enter, 7 times, and 1.8 0.76, enter 0.64 times plus, and 0.0416, enter 0.09 times plus. Got 0.526. Is that what y'all are getting? Okay, 0.526. Anybody have a number for blue? We don't have to do this. Say that louder, please. Okay. Does everybody agree on that one? Okay, and so then this is the one that I was talking about. It's greater than 1, so we could just truncate this at 1. It's a max at 1.0. So the 8-bit R is equal to 255 times 1 equals 255. The G is equal to 0.526 times 255. I did that kind of backwards, but it's fine. And then the blue is equal to 255 times 0.003. So 6, 134. $255, enter 0.003 times 0.76, so we'll round to 1. Okay, so that gives us the 255, 135, and 1, so answer A. So I'm so glad we got it, because that's a whole lot of tedious work to get one answer. But notice this one is wrong, because this used the 1.24. And so it's maxed out at since it's 8-bit, the maximum value is 255, so it can't go above 255. So you could have calculated 315 and then just brought it down to 255 and said that's the maximum value, or you could have truncated it at 1, and so you can do it at either step. Yeah. Since we're here on this page, let's look at the tristimulus values. So the chromaticity coordinates are the little x and little y. So little x is equal to the capital X over x plus y plus z. And so then that would be 0.7 over 0.7 plus 0.64 plus 0.09. Enter 0.64 and 0.09. So the sum on the bottom is 1.43. So 0.7. So 0.49. So little x 0.49. So that's the x value on a chromaticity diagram, and then the y value is equal to 0.64, the y value over 1.43. 0.45. Yeah, so that's what we've got here. So that's the math on those two. Now, I mean, around, I don't know, around, depending on the different illuminants, right? Whether you have an A or a B or a D65 or D5, D50, the white point, like in the chromaticity diagram, the white point will move slightly because like the A illuminant is more yellow. It's the incandescent light, and so you'll have. In fact, let me just look at a chromaticity coordinate diagram. Let's see how I can show this on the screen. Which values? The matrix? Yes, for sure. Yeah. Yeah. I mean, that'd be silly for me to make you memorize that. Yeah. So I'll put it on the equation sheet. Yeah. Um, yeah, let's look at the chromaticity coordinate diagram. Bless you. Goodness. Let's see. Let's go here. No capture. Cool. Yeah, there we go. Okay. There's a whole bunch of different ones. Let's look at, yeah, this one's got the um, the white point movement here. But anyway, we've got the chromaticity coordinates of, let's go to Wikipedia page here. Let's look at this guy. Okay, so we calculated the chromaticity coordinates was it 49, and it was 0.49 for x, right? Look at your notes. And what was the y? 4.5. Okay, so we're can't reach there. I can use the stick. Where's the stick? Okay, so here's 4.9, right, and 4.5. So 4.9 and then 4.5, kind of right on the edge here. So it looks like we have an orange substance. And so you can use, this is very quick to determine what the general color of a substance is if you've got the chromaticity coordinates, the x and y values in the chromaticity diagram. Notice this white point here in the middle, that would be kind of a function of the illuminant. And then this curve here is the black body radiation curve. That's kind of what the source would look like if it was a black body radiator at 4,000, 5,000, 6,000, 10,000, and so on. So maybe you've seen the jet engines and so on as they're coming out. They're really, really blue. I mean, we're talking about 10,000 Kelvin coming out of the back of those jet engines. Now, sometimes they're more orange and red. It's because of the afterburners. They're just dumping tons of fuel after the turbofan, and we have some unburned carbon. But the inductively coupled plasma is super bright white and almost has a blue tint to it. I don't know if you've ever seen that. There's one over in TRIS where they atomize the atoms and get the optical emission from that incredibly hot plasma. And from instrumental, you probably should have learned the different temperatures for the different instruments. Like the flame AA is around 4,000 to 5,000 Kelvin, but then you get to the inductively coupled plasma and you're at 10,000. Arc spark can get you up to 50,000 Kelvin. So you would have a different perception of the color based upon the temperature of those hot objects. So that's the chromaticity coordinate diagram. I like them because they're fast. You just have 2 points. You go in there and see what color you have. Okay, let's go back. It won't let me do it. Let me close this guy. Doing all this for the video. Okay, let's go back to PowerPoint. There we go. Nice. Okay, we're back. Next question. I'm always trying to find different pictures of gunshot residue and pollen, and so we could we could look at more pictures of pollen and stuff like that. But I would say that's a good way to study is to go on the internet and look up images of gunshot residue and look up images of pollen and things like that. So you just get more familiar with the different pictures that are out there, size scales and so on. Nowadays it's pretty impressive. They can isolate those pollens and then they can I don't know how much sample they need, but they can get the DNA profile for the pollen grains, and then they can really match the they can really individualize those different pollens. 13. Okay. 4 and 5 on 13. Yeah, okay. That's good. So here this in this image we've got a whole lot of information. And so we have, again, this is transmission. So you always want to check to see if this is transmission or absorption. Because now that we know this is transmission, this is 100% transmitting. And so this, when the curve is up here like this, that means this light is transmitted, right? And then you can look at your spectrum that if you're looking at wavelength, then it's red, orange, yellow, around here, around 600 yellow, um, green, blue, I guess, indigo, violet. So there's your Roy G. Biv. And so this edge wavelength is right here between the blue and the green. And so only blue light is transmitted. Okay. And so what color is this filter? It's blue because that's the only light that's transmitted through that filter. Okay. So the above spectrum is what kind of filter? Well, look at the wavelengths. These are the shorter wavelengths. And these are passed. Why did I write a B? So the short wavelengths are passed, and so this is a short pass filter. Okay. It could also be the low energy wavelengths. No, I said that wrong. That's high energy, sorry. High energy. So the high energy wavelengths are passed, and so it could be a high pass filter too. Short pass, same as high pass. If you were to invert that spectrum and it was passing the long wavelengths, it'd be a long pass filter. And those are the low energy, so it'd be a low pass filter. So those are the same thing. A band pass filter would go up and then back down. So it would pass a particular band of light. And so that's what a band pass filter is. An interference filter, let's say we had an interference filter at 600 wavelength. It's a bandpass filter, but it's really sharp, like that. So it's using interference, and it only applies to a very narrow region of wavelengths because you're looking at destructive interference of the wavelengths. So particular wavelengths and the thickness of that filter are going to bounce back and forth, and when they bounce back and forth a certain number of times, they cancel each other out. So that's good. And I'm always looking for different, like you saw on in the notes, maybe a little bit better looking graph. This is the old graph that I was using, and so yeah. But you always work with the axes first. Find out what's being plotted. Let's say it was absorption, so we're plotting absorbance and wavelength. Okay, it would have very low absorbance down here in the short deal, and then it would jump up like that, and And so here in this case, because we're dealing with absorbance, okay, we're absorbing the long wavelengths. We're not absorbing the short wavelengths. And so this would still be a short pass filter or a high pass filter, but it looks the opposite because we've got absorbance here. Yeah. And so we're looking at what light is absorbed, not what light is transmitted. And so when there's low absorbance, that's the light that's going through. Okay. Hey, you made it. Yes. Yeah. Not the exact, and I try to make them like obviously right, because I don't want to get in an argument and say, well, technically that's yellow, not orange, So if it, like the yellow orange region is really, even in my estimation, kind of tricky to suss out, right? But green is clearly like think of 532 nanometer light. So 532 is that green neodymium YAG laser that you maybe you've seen before. It's this green. It's like the brightest green you've ever seen, and that's 532 nanometers. So that's definitely, yeah, absolutely. That's a green color, um, and it's on the look here. It's on the reject side. It's on the not transmitted side. So this is clearly not green. Um, if you had an edge wavelength right at say 532, again, it's absorbing half of that green. It's going to be a blue or red. Now, what if we had the opposite of this? If this came up and it went like this, we're getting red and we're getting orange and we're getting yellow. Okay, if you get all three of these, you see the shortest wavelength one. You see yellow. Okay, if we move this over and we cut out the yellow, and now we're getting the orange and the red, we see orange. Okay, the only time you really get that color red is if you cut out the yellow and the orange, then you just have the red left. So if our pigments in our eye get anything other than the red pigment, then it starts saying, oh, I perceive that as orange, or I perceive that as yellow. Um, yeah. Even if you cut out just a little bit of the blue, um, let's see. I guess you get kind of a dirty yellow, a greeny looking yellow, but yellow is a pretty dominant color. The only way you get green, this is getting to be a very messy picture. Let's do green. Okay, I've got an eraser. Okay. So this would be green. This would be something that absorbed the blue, gave you a little bit of green, and absorbed out that red. So this is the only thing that you would ever see for green. Like you would have to have green and no red and no blue. So you're not going to see green if it looks like this, right? We're getting a little bit of green, but we're getting that yellow and that orange and that red, and so we're going to see that as yellow. Yeah. It has to get rid of the red so that you can see green. Yeah. Yes. That's a good question. I really don't know. Yeah, I really don't know. Um, the only time we really get that violet color is when we really start taking out the blue and we just have 400 nanometer light or even less, like 365, those UV lights that I have in my lab, they're definitely purple or violet looking. Um, And so maybe it's not the shortest wavelength. Maybe it's more governed towards being biased towards the middle, because we have those three pigments. We have a blue pigment, a green pigment, and a red pigment. And this, what I've drawn here, is pretty much that Y observer function that we call green. And so maybe it's just biased towards whether we include the red and the green pigment and we call that yellow, or if we incorporate the blue and the green and we call that blue. Um, but if we get rid of the green and we start getting a really low response on the blue, we perceive that as purple. So maybe it's just sort of biased towards the middle of the visible range. I don't know. That's hand waving, but yeah. But what I'm going to do is I'm going to be trying to give you the obvious ones. Like I might give you a green one because then the red's gone and the blue's gone. Or I might give you the blue and you're like, well, I don't have any red, I don't have any orange, it's got to be blue. You know? Or the red, I don't have any orange, I don't have yellow, so it's got to be red. Yeah. But that's enough for you guys to like force yourselves to be familiar with the colors and the, you know, like I said here, this I don't have it very specific here either. I've just drawn the letters down here. Um, you know, whether orange is at 650 or really like 630, I don't know. I'd have to go and check online and see, you know, look for an alignment. They have that chromaticity diagram. You can see the wavelengths all the way around the outside of that chromaticity diagram. So you might look at that too. Other questions? Oh yeah, yeah, yeah. Stick to the homework, but honestly, the like all of the monomers, that page with all of the molecules there, um, it would really be good to like a lot of times I'll give you five molecules and I'll see which one of these is like a synthetic chloro, what does it say? Synthetic chlorofiber, whatever produces a chlorofiber, and only one of them has chlorine, right? So you're like, okay, it's got to be that one because the chlorofiber, right? Um, the you know the styrene molecule, the ethylene, polyethylene, yeah. Well, I'm saying, yeah, you'll have five of those monomers, and you'll have to figure out which, you know, which one of these, like which one of these produces polystyrene. So you need to know which one is styrene. It's the one with the benzene ring that's off to the side. Um, if I have like, um, what was it? It was like ethylene glycol and bisphenol A or whatever to make, um, no, it was a diamine. I'm trying to remember from my brain the two pieces that made Kevlar. Anyway, you know, but I like those questions because there's, you know, you have five molecules and then you can pick. It can be multiple gas, not multiple gas, multiple selection. That's the one, and 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 so on. You know, it's different properties of those. Yeah, was that the last one? 11? Yeah. You can tell I'm not big on the 500-watt xenon light source. I really like the LEDs. Yeah. Problem is you have to have a suitcase to hold all the different wavelengths if you want to be selective. Our little LED lights that we have in the lab are, not what we're talking about here. These things are pretty large and last a lot longer, give off a lot more light. Does it talk about streamers in here? Let's see. It's carpet, donut pattern and carpet for sure. That's a pool fire. But there's also streamers where they run, maybe they run gasoline in a stream to connect multiple rooms. That's a telltale sign because that's not a natural burn pattern when you have a really narrow trail of burning. If the origin of the fire looks to be the middle of the room, why would the middle of the room just catch on fire? I mean, if natural fires would start near sources of energy, what a source of energy would be the stove, would be a electrical outlet, a wall switch, or something like that. So you would look at those kinds of physical pieces of evidence. Did y'all like the Molotov cocktail? Slurred speech. Have fun with this. You gotta have fun, right? There was some question on the Full Metal Jacket one because there was two answers. It was A and E. Because again, the lead of the bullet. I mean, why use lead? Well, think about it. What is the kinetic energy of an object? It's 1/2 mv squared, right? So that adds the m. So it's really just that it's a heavy metal and it's cheap. So lead is literally dirt cheap. You can just get it right out of the ground. Um, very low melting point, so easy to manage. Okay, but then that increases the mass, which increases the kinetic energy of the bullet, and then that's imparted to the thing you're shooting. Okay, um, but then this small cartridge, the rifle cartridge E, is going with the velocity, so it's got a smaller bullet but a much higher velocity. And again, energy is velocity squared, and so that really ups it. So if you could cut the mass of the bullet in half and then double the speed, then you have 4 times the energy. Yeah. So anyway, so let's see, you cut it in half, so that cuts the energy in half, but then you double the velocity, so that squares it and then brings it up by 4. So actually it'd be an improvement of 2 times. Yeah. So these other 3 are the right 2 are hollow points. I mean, it should be obvious. Like right here, the point is hollow. You see that? Okay, but this has a little ball in there that helps it expand. So technically, I think this is also called a hollow point. It's got that little ball in it, and all that is just to help the expansion. We get a Yeah, I would be looking for you to include B, C, and D on those. Yeah. Um, yeah. They this one with the ball, my understanding is that was a special round. Now everybody can buy it, but it was a special round developed for air marshals. Okay. So if you think about, you've got a terrorist that's trying to hijack the plane and you need to disable this person immediately. You want to shoot them, right? If you're an air marshal, but you don't want the bullet to go through that person and injure someone on the other side, or even worse, the plane, and injure potentially everybody on the plane. And so this was a way to have extremely rapid expansion and delivery of the energy of that round to the person, the first person. So it expands rapidly, delivers all of its energy to the first person and doesn't penetrate through and create a risk behind them. Because if you think about the airline, I mean, everybody's in front or behind someone else. So you don't want like E up there. That's going to go through four people, you know, and so that's not what you want. So you would want something that's going to expand rapidly and deliver all its energy to the first person. They could be, yeah. They may not expand rapidly enough. And so if they don't expand rapidly enough, they don't slow down. So it's the expansion that slows the bullet down and delivers all of that energy to the person that's been shot. Yeah, it's gruesome to talk about, but that's a perfect example where you really need that. It's just not just about committing a crime, it's about protecting people. And if somebody needs to be stopped, then you want all that energy to be delivered to that person and not put anybody else at risk. Yeah, yeah, yeah. And so there's a lot of different kinds of rounds. Now there's some really exotic shotgun rounds for home defense that are absolutely crazy in the way they expand. And of course, they make this ballistic gel. I don't know if you've ever seen that, where you can video the effects inside the ballistic gel. So it's dense enough to let the bullet, stop or slow down, and you can see the impact and the energy delivered to that gel. And the slow-mo guys are great. They have these high-speed cameras, and you see the gel. Sometimes it'll expand, this much as that energy is delivered to the gel, and then it'll come back down, and they'll catch that on video. Yeah. Okay. It's a terrible video. Too much dead air. I may just put this one on blackboards. Well, if you have no more questions, we're good. Now, the way it works too is that after the exam, then I'll grade them and I'll post the grades. I'll pull in, attendance and homework and all that stuff. I'll make sure everything is up to date. Um, I'll the quality report won't change your grade very much. I mean, let's say, okay, maybe if you're like 1/10 of a point or a half a point from a letter grade or something, but for the most part, after this third exam, I'll update your letter grade, and if you're happy with that, you don't have to take the final. Okay. But if you take the final, it goes into your full exam percentage, so it can go either way. So, but if you want to shoot for that next letter grade, then I encourage you to do that. But if you're happy, you're good, you want to focus on other classes, that's my gift to you as graduating seniors, and so you can do that. Yeah, for sure.